So limits of functions of several variables. We'll focus on, let's say, functions of two variables in this class and tests, but these ideas hold for functions of three variables and higher. We say a function f of xy has limit L as xy approaches AB. I guess maybe I'll actually verbally you would say at AB. If the following is true, informally, the value of f of xy gets closer and closer to L if xy gets closer and closer to the point AB. All right, note that oftentimes your functions might have a domain that does not contain AB, which means you cannot actually evaluate your function at the point AB, which is why we have this idea of limits, right? Limits are more general than evaluating functions at points. You can oftentimes not plug in AB to your function. You could only see your behavior of your function as xy approaches AB, right? So note that AB may not be contained in the domain of f, so you cannot just plug in AB. All right, so now formally, more rigorously, we say the following is true. So I'm going to put some scary Greek letters here, but we don't actually need to know this for in any sense when you're actually doing the exercises, but it's important that I think you see this definition at least once. So for any small positive number epsilon greater than 0, all right, this is just, you call it K if it makes you feel better, but epsilon is a traditional for this notation. We can find another another positive number, delta, usually small, delta also greater than 0, such that the distance or the difference of your function value and your limit L, so this is the absolute value of the difference, is less than epsilon whenever the distance between xy and the point you're evaluating the limit at is less than delta. All right, so to recap, we say that a function has a limit L, a limit 3, let's say, at the point 0, 0, if I can make my function as close as I want to 3, so long as my distance from 0, 0 is less than some number delta. All right, it means I could squeeze, in essence, my domain, my area around A and B as tightly as I want, and I can restrict my function to take on values as arbitrarily close to L as I want. Does that make sense? Any questions here? Let me do some clarification. You've seen the distance here is also notated. This is equal to the square root of x minus a squared plus y minus b squared. So you sometimes see this notation as well. So whenever this quantity is less than delta, so whenever xy is delta close, right, its distance from whenever xy is has distance less than delta from AB, your function is distance less than epsilon away from L for any positive number you want. All right, so you can make f, if I want an estimate, I want to make my function as close to 3 as I want, I can make epsilon 0.000005, and I'm saying that if my function truly has a limit 3 at 0, 0, then I can make my function values be as close to 3 as I want. Its difference with 3 is going to be less than 0.000005 whenever my distance from the origin is less than some delta. All right, if you're able to do this scenario and carry this through, then your function has a limit. Yes, we'll try to. So we're not going to work that much with this definition. All right, what we're going to do instead is I'm going to show you several examples of functions with no limit, and then we're going to look at two particular, I guess 3, but really 2 ways where you can assure yourself that there is a way where you could use this tool and technique to find whether a limit exists or not. But I'm actually not going to stress too much of doing this with numbers because that's bringing us a bit far off course. But I do feel it's important for you to see this at least once. So that's why I've brought this. I showed this notation here. But let me maybe just illustrate one thing. Maybe if I draw schematically the domain here, right, of what your function is, and here's what your so you have a function f of xy, and there's a range of f and xy. Then we say there's a limit if, right, let's say there's a limit L if whenever I restrict myself to, say, an area here, let's say this is a ball of radius delta, then I could actually, so long as I'm within this ball, I can't, it's a punctured ball, really. I can't really be at the point AB, but anywhere within here is going to assure me that I'm within epsilon of L here. All right, so this is epsilon away from L. Okay, so that's, visually speaking, that's what I'm saying. And you could sort of argue that, well, this is telling me that, as I approach also, however I approach A and B within this ball here, I'm always going to end up approaching L. Okay, but the key step here is there are many ways to approach AB. So how to find limits or show they don't exist. That's the next topic that we're about to do now. Because as you can see, this is a very abstract definition. It's very rigorous in the sense that it's very clear what it means for you to have a limit at a point. But in actuality, this is a condition that's incredibly hard to verify. Let's deal with how limits could fail to exist first. All right. So failure of limits to exist. The most common one, especially in this class, is because they're the usual ones where, let's say you have a function which just completely it's badly behaved. It's like it's very clear where no matter how you approach the origin, it's going to go to, say, infinity. All right, so then your limit might not exist, right? If your limit is infinite, then there's no real number that will happen. So for example, if you have a function like 1 over x squared plus y squared, then your limit's not going to exist because you're not even bounded anywhere near the origin, right? So there are the obvious examples that, say, generalize from one variable. So for example, let's say f of xy you could take as 1 over x and take xy goes to 0, 0. Well, then it's the same thing as in one variable, right? You're ending up x goes to 0 and you blow up in a sense, right? You blow up in different ways, right? As x approaches 0 from one way, it goes to minus infinity. The other way, it's plus infinity. Either way, it's not something finite. Now the more subtle in this class, let's say f of xy, let's say as xy goes to AB along different paths, f of xy gets close to different numbers. So let's see here, right? Let's take a look at a few examples. The first one is, let's take g from our example that we saw on the table, which I can't share anymore. But remember that we had the second table we saw earlier. It was for the function x squared minus y squared over x squared plus y squared. And we saw using the table of values that, in fact, there were severe issues with how you with a limit existing. We conjectured that the limit doesn't exist, and now let's see why. Does the limit? Oh, I can't believe I forgot this, but the notation here, let me scroll up a bit, is maybe just fix this in your notes. If a limit exists, we say the following: the limit as xy goes to AB of f of xy is equal to L. Or you also see this notation sometimes: f of xy goes to L as xy goes to AB. All right, that's the actual mathematical notation or shorthand for limits existing. Okay, so does the limit exist as xy goes to 0, 0? Well, one thing you could do is, which is replicated, we're going to replicate what we did visually looking at the table of values, is if we approach along, let's say, x equals 0, right? So Here's our point 0, 0, and the xy plane, not in our domain. We can approach here along x equals 0. So that's along this axis here. So in this direction of approach, let's see what this function is. We plug in g of 0, y, is going to be equal to minus y squared over y squared, which is equal to minus 1. All right, so this means that the limit as y, so this is now a single variable function, right? So single variable function of y. And now the limit of y as y of g of 0y as y approaches 0. What is this? Right, it's minus 1, right? It's a constant. So remember if you forget this, maybe as a quick refresher, just look back at your calc 1 notes, right? Limits to constants, always constant. So it's minus 1. If we approach along, let's say y equals 0, you got a similar thing. Someone in chat, does anyone want to volunteer what this limit ought to be? Well, I guess you could just remember from the textbook, but in this case, what's a constant function? Well, g of x 0 is x squared over x squared, which is 1. So limit along the x-axis, all right, which is what we're taking here, is equal to 1. Now, 1 is not equal to minus 1, clearly. So this means that the limit cannot exist, okay? So the moral of the story, if you can find two paths to A, B, where I'm going to be informal here, but I'm going to call it the path limit, don't agree, then the limit of f as a two-variable function does not exist. All right, and in this class, this is probably one of the main things you could take away, because you're going to be looking at a lot of examples where we're going to ask you if limits exist or not. And by the examples I'm showing you right now and in class and in tutorials, you should be able to test some paths and figure out if the limit exists or does not exist. Any questions so far on this particular example? We're about to do a couple more. So let's do another example here. By the way, we could have also plugged in x is equal to y, right? We didn't need it here. We found two paths where they were equal, where they were already not equal. So the limit cannot exist, but we could have also just checked x is equal to y, right? At x equals y or x equals minus y, this is x squared minus x squared, right? So that's 0. So the function's just 0 along these. That matches what we saw on the table. So we could also just have seen that when you approach these diagonally is completely different. Okay, so let me answer a few questions in chat. When I inserted 0, was it because of the point 0, 0? Or we could just find any path. And I just plugged in 0 in this particular case because it was an obvious path to 0, right? Certainly, if I want to have a path towards 0, the axes are very valid paths towards the origin. So these are the, you could think of this as like the most obvious paths to 0. So one question you get is, I don't get how it doesn't exist because we have to input different values when we are inputting. I mean, you have different values when you're inputting, but remember, the definition of a limit here tells you that if a limit truly exists, it doesn't matter what direction I approach A, B in, right? If you look at this visual picture here, so long as I'm confined to within a distance, right? Remember, a distance is agnostic towards how you're arriving at this point A, B. I could arrive it along any arbitrary, like a spirally path, a straight line path, a diagonal path, whatever you want. So long as my path is within this turquoise ball, delta, I should make sure that my value is arbitrarily close towards the limit L, if a limit L exists. So the definition of a limit itself in two variables and in any number of variables, it's agnostic. It does not care how you approach the point, all right? It's a very strong condition. You could if you approach a point this way, and you get, let's say in our example, you approach this way, you get 1, and you approach it this way and minus 1, that's not okay, because how is it possible for you to be arbitrarily close to a single limit if when you're arbitrarily close along this direction, you're always stuck at 1 or minus 1, and here you're always stuck at 1, then there's no way for you to be infinitesimally close to A, B and approach at a single value, because 1 and minus 1 are they're always fixed. They're really far apart. So how does the case x equals y show that the limit does not exist? It doesn't exist because in this case, as a bonus, right? Here we've tested two paths and they're different. And so long as you have two paths that are different and they give you different numbers as you approach the point on a path, your limit cannot exist. So x equals y doesn't really tell you anything more. All right, it just tells you that in this, I could have maybe instead of taking the second one here, I could have substituted x equals y and gotten 0 and say, okay, 0 is different than -1, so that's also good enough to tell me that a limit doesn't exist. All right, so let's take a look at the following. We have the same situation here. Let f of xy be the following: xy over x squared plus y squared. Does the limit exist as xy goes to 0, 0? Okay, so in this case, what happens when you plug in x equals 0, y equals 0? So once again, let's try and repeat what we've done here so far. So here we set in x equals 0 for this axis, y equals 0 for this axis. What happens if we do the same thing here for this function? So let's say on x equals 0 or y equals 0, what happens? Does someone want to volunteer? So without being in the origin, right? So you're away from the origin, but you're on either x equals 0, y equals 0. So I plug in x equals 0 to this function, what happens? So I plug in x equals 0 here, what is this function? Right, so this is going to be identically 0. They're always 0, right? Because, so long as one of these is non-zero, well, the top part is always going to be 0, and then you're going to be dividing by something that's presumably non-zero on these axes. That's not the origin, so you're always 0. So it looks like along these terms, along these axes, along the axes, it seems f of xy approaches 0, right? If it's constantly 0, then along here, when you travel along here, the function seems to be at 0. Okay, but let's try and do a more interesting line here. So let's suppose we approach it on y equals x. All right, so that's this line here, right? This path here, y equals x. So on y equals x, you could plug in, let's say, just set x, x is the same thing as y, so we could just set f x of y. Well, we plug in one of the variables, that's just, let's say, y or xx if you want. Same thing as x times x over x squared plus x squared. This is x squared over 2x squared, which is 1/2, right, away from the origin. All right, so everywhere outside the origin here, you're along 1/2 here. So does the limit exist? So the limit does not exist because we just found a path here, and this particular diagonal path, where you approach 1/2. However, we found another path. In fact, we found two paths, either this one or this one, where your limit along this path is 0. So your overall limit, the limit of the function, does not exist. So this means that does not exist. All right, guys, let's continue. So far, we've seen two examples of limits not existing, each more subtle than the other, right? The first example, we did some very obvious cases on the axes, right? Right away, we plug in the axes, and we found they disagreed on the axes. On the second example, we plug in the axes, they actually agreed on the axes, right? If you were to take these directional limits, as you might call them. However, when you go off when you go off axis and say take a diagonal line, then you have a disagreement. So let's now take a completely different example, which is following. Let's take f of xy is equal to xy squared over x squared plus y to the 4th. Does the limit as x and y approaches 0, 0 exist? So let's actually do something in general here. Remember that so far we've tried the axes, we tried basically distinct lines, but let's try and do lines of all slope at the same time. All right, so let's first consider any line through the origin. Sorry, the qualifiers should be different here. Any line through the origin, y equals mx, right? So these all go through the origin and m is the slope. So if I plug in y equals mx to my function, what do I get? Does someone in chat want to reply? So remember, we want to do the substitution. Y is now equal to mx. So I put an mx here and I write this. What do I get? All right, so if I plug in y equals mx on the top, I would get x times m squared x squared. And on the bottom, I would get x squared plus mx to the 4th. I get m squared x cubed over x squared plus m4 x to the 4th. Now I can remove a bunch of these powers, right? So I get m squared x over 1 plus m to the 4th x squared. So now let's take the one variable limit as x goes to 0 of this function here. Remember, this single variable function is is given to us by restricting our two variable function on the single line, y equals mx. What's the limit of this? So far, this limit looks like 0. And this is pretty general, right? This holds true for every single slope m. So we've maybe not done the parallel line, right? But if you do plug in the parallel line, the vertical line rather, the vertical line, the y-axis, so that x equals 0. If you plug in x equals 0, this is also 0. So in fact, it looks like every single possible straight line going through the origin, these straight line paths all have the same limit 0. So it looks like we're in pretty good shape. But here's where sort of the infinite paths deal comes in. Let's try and approach the line in a slightly different way. All right, let's consider now a parabolic path through this. So this is a parabola x is equal to y squared. All right, now consider the parabola x is equal to y squared. So in this case, if I plug in x equals y squared, my function, so this x is now equals y squared and y. And so what is this? This gets me y squared times y squared up top. And then I have y to the fourth plus y to the fourth on the bottom. This is y to the fourth over 2y to the fourth, which is a half, which tells me that the limit as y goes to 0 along this parabola, right? So if I along here and approach 0, it's a half. Does the limit exist in this case? No, right? So 1/2 is not equal to 0. So this means that the limit does not exist. All right, so things aren't looking good for us because it looks like we've been a bit more ingenious in this case. We've taken an infinite number of lines now, right? We've literally every single possible line going through the origin, we've checked, and we could verify that along each of these lines, the limit along each of these lines are 0, they match up. And yet, as soon as we take a curvy path, a very simple curvy path, if you will, right? It's a parabola through the origin, it's a half, and everything falls apart. Moral of this story, great. So moral of this story is it's very hard for you to decide using this method on paths to verify whether a limit does exist or not. In this class, we're going to teach you, well, mainly two versions, 2.5, I'd say. But the main idea here is I'm going to go through in the following steps techniques that we'll learn on how to assure yourself there is a limit that exists. And when this comes up in tests or exams or homework, it really is we're restricting to sort of a lot of functions end up looking like this or similar ones. You're going to have to try basically the techniques we give you. If none of the techniques we give you to assure a limit exists work, then your task is in order to definitively show it doesn't work, you'll have to substitute in either lines or maybe parabolas or maybe something like x equals y cubed to demonstrate exactly why the limit doesn't exist. So to prove that a limit exists, you cannot use this path method. There are infinitely many paths. We can't go through infinitely many paths to show that every single possible path is the same. So moral, we can't check infinitely many paths, or maybe we should say restricting on paths is a bad/useless way of verifying a limit existing. There are infinitely many paths to check. Instead, right? However, I guess the converse of this, or the contrapositive of this, is checking on well-chosen paths is a good way to show a limit does not exist. In essence, here's the game, right? And especially when it comes to homework and tests, you're going to see rational functions a lot that look like this. In this case, how do I know this was a good path to check? If I set x equals y squared, then look at the ratio of the powers in y and x here. This is y to the fourth x squared, y to the squared x to the 1. All right, the power in y is always 2 times the power in x. When you see something like this, or when there's a relationship between the powers of y and x, it's a good idea to restrict onto the curve satisfying that relationship and seeing what happens. All right, a lot of the times, because of how these functions are cooked up by your textbook and a lot of times in exams, when you have differences like this in powers that are constant up and bottom, you should try plugging in something that puts x and y on equal footing, all right, in the sense here, right? When we put x equals y squared, you suddenly get a single variable function where it's just all in the same power, and these powers have a chance to cancel and get you something constant. And your hope is, this constant here is going to be different than, say, just restricting on lines, in which case, in this case, it is. And then you get a very easy proof of why a limit cannot exist. All right, so whenever you see something like this, or a function where the methods I'm about to teach you are not effective, it's worth trying to find explicit paths where your limits, where the path limits fail to agree with each other. All right, so that's usually the game. So how to check when limits do exist? So one, the very cheap way of this, right, is it's stupid, right? If you have a polynomial or like a rational function, let's say you have a function like this, and your point is not 0, 0. Your point is in the domain. Your domain, your denominator here doesn't vanish. Then you just plug it in, and that's what your number, that's what your limit is, right? I could just, if this were 1, 0, I just plug in 1, 0 and see what I get, and that's my limit, right? So that's sort of the half method, right? I'm not going to count that as a method, but I might as well record this down. 0, method 0. If f of xy is a polynomial or a rational function, and ab, for the rational function at least, does not make the denominator 0, then the limit is exactly what you would expect, right? You just plug in a and b, right? That's really stupid, right? This holds true for any function that's very nice, right? If you don't see an obvious problem with a function to plug in ab, then you put it in and it seems like it works, right? So that's kind of stupid. Okay, so let's not spend any time on that. Let's do method 1, which is the squeeze theorem. All right, and so let me try and find I'd written something down for the statement of the squeeze theorem, but all right. So we did this in one variable, right? And the one variable case, what we had was something like, let's say, well, let me just state this in two variables first. So suppose we are given a function f of xy and want to find its limit at ab. Now, a statement is if we can find functions g, let's say h1 xy, h2 xy, such that f of xy is always in between these two functions for all points near the point I want to find the limit of. And let's say the limits of these other functions all approach the same thing. So h1 approaches L and h2 approaches L. Then your function trapped in the middle, your original functions that you started with, must also go to L as well. So let me remind you, in case you maybe forgot this in one variable, we had an example of this in one variable here. And the question is, does the limit as x goes to 0 of, let's say, x squared sine of 1 over x exist? If so, what is it? And so what you have here is in our notation above here. So in this case, our function that we care about, we're given, is x squared sine 1 over x. And now we note that, observe that sine of 1 over x is always, for x not equal to 0, clearly, but what is this always trapped in between? Right, it's always between -1 and 1. So this means that we have the following. We have x squared sine of 1 over x is always less than or equal to, if sine of 1 over x is always less than or equal to 1, then certainly this is certainly always less than or equal to x squared. And similarly, it's always greater than or equal to minus x squared. Right, so these here are, this is h1 of x in my notation above, and this is h2 of x. Now, what's the limit of x squared as x goes to 0? It's 0. We have these facts here, and by the squeeze theorem, this means that the limit exists and is equal to 0. Any questions here on this one variable example? All right, so let's do a two variable example now. So, I mean, the way I frame this now, the question is always, the answer is probably going to be yes, it does exist, but on a test or something, it's going to be less obvious. So let's try the following. Xy to the fourth over x to the fourth plus y to the fourth. And we're going to take this, well, the difficult limit here is at 0, 0. So does this exist? And if so, what is it? So what might I care to squeeze in this case? Or squeeze with? So what if I write this as this is equal to x times y to the fourth over x to the fourth plus y to the fourth. So we can't really cancel out the denominator in this case, right? We can't factor out really anything. So maybe take a look at this quantity here. This quantity here, what's that bounded by? I have y to the fourth over y to the fourth plus x to the fourth. Now, what x to the fourth, could x to the fourth ever be negative? Right, so this could never be negative. So I have something plus something, the same thing, by the way. Let's just call this blah. I have blah over blah plus something positive. Now, is that always less than 1, equal to 1, greater than 1? This quantity here. Right, so note that this is always less than, well, it's always less than or equal to 1, right? It's equal to 1 precisely when x is 0, but we just do this here. And could this ever be negative? Right, so this could never be negative, unless I guess y is 0. So it's, that's when it's 0. So it's greater than or equal to 0. So what could I squeeze this quantity by here? So I have my function here, that's x y to the fourth over x fourth plus y fourth. What could I squeeze by on the left and right of this? Right, I could squeeze this by 0. I could squeeze this by x, right? X here is from the x times the upper bound 1. Okay, so this left-hand side, this is always a constant, right? This is a constant 0, so the limit is 0. Here, the limit of x, this is 0, and the limit of x is also equal to 0, right? It's just x. Okay, so this means that by squeeze, this goes to 0, as xy goes to 0, 0. So on a test here, right, it's important for you. I mean, you could maybe guess at some of these and guess that they're 0 or whatever, but it's very important for you to get full points on a test or an exam that if you're applying the squeeze theorem, you can't just say, oh, squeeze it and it gets to 0. You need to be pretty explicit on what you're squeezing it by, right? In this case, we've squeezed it by 0 and x because of this bound. So it's very important for you to clearly justify why you could use the squeeze theorem and what precisely are the functions that you're squeezing your limit. You're squeezing your function by in order to get the limit. So squeeze theorem is one major tool that you have at your disposal to find what a limit is. And another way of doing so is use polar coordinates. So what do I mean by using polar coordinates? So remember, in polar coordinates, let me draw the schematic here for you, right? So in polar coordinates on the xy plane, everything is sort of is described instead by the distance given to you by r from the origin and an angle theta, right? Now, what makes polar coordinates nice is, I should mention this, is especially, you use this in most cases, all right, when your limit that you're evaluating is at the origin. And what makes this nice is oftentimes if you have any sort of symmetry in your problem, you could reduce powers of x squared plus y squared directly to r squared. And r is really the distinguishing feature of what it means, right? If you have what it means to have a limit when you approach 0, 0, right? R here, literally, if you just completely disregard what theta is in polar coordinates, constant r is just a circle of radius r. And what it means to have a limit at 0, 0 is precisely when r goes to 0, you want your function to have, to distinguish a value, irrespective of what theta is, all right? Right, because if you look at the definition of a limit, right, it's just a limit L exists, let's say A and B is 0, right? Whenever x and y is sufficiently close, if you can make your function take on a value very close to your limit, whenever your distance is less than delta. Your distance here is r, all right? So when you're evaluating limits at the origin, and you switch to polar coordinates, what you're looking at in r is quite literally this quantity here. So it's really directly tied to your limit definition. it's agnostic as to which direction you come into, because you're completely ignoring off theta. And if you have a function which you could just read off the R information from without theta, and it all gives you the same, it always gives you the same answer, then your limit exists. So that was a horrendously explained concept. Let me try and do an actual example. So here's the problem. Let's revisit that very first example we saw in the textbook, which was the first table, right? The first table had a function f of x, y, which we decided based on the table non-rigorously that we thought it looked like the limit existed. All right. And that function was sine of x squared plus y squared over x squared plus y squared. So what is this function if I write this in polar coordinates? What does x squared plus y squared become in polar coordinates? R and theta, right? It's just r squared. So in polar coordinates, let's say f of an r of theta, this is sine of r squared over r squared. So the question now becomes, does the limit as r goes to 0 of sine of r squared over r squared exist? So there's a subtle difference here. It's not quite sine x over x modified, right? R, first of all, is never negative, but it's pretty close. So what's the answer here? How might you do this in one? So this is now a function of one variable. It's just r. So how might you attack this? What's the rule that you want to use from one variable calculus? Remember, at r, the denominator here goes to 0. The numerator also goes to 0. So how do you do this? This indeterminate form? You would apply L'Hopital's rule from one variable. So the limit that we want, it's the same thing as if you take the limit of the derivatives up top and bottom. So this is 2r cos r squared over 2r, right? So these cancel out, and this is equal to 1. All right. So what does this get me? This gets me, converting back to the usual variables, this tells me that limit as xy goes to 0, 0 of this function, just like we saw in the table, it seemed to converge to 1, and here we just proved that it converges to 1 by switching the polar coordinates. All right, what does switching to polar coordinates do? It completely eliminates the directional issue here, right? How the direction that you come in, the infinitely many paths that go into the origin, really, you could parameterize those paths by r and theta. Theta being like the angle at which you're approaching at each point, and r is just a distance. But when we're taking the limit here, and r goes to 0, that's really what we mean when we're taking the two-dimensional limit, right? We only care, we're completely agnostic on the direction you come in for any possible theta that you come in at. If you converge to a value independent of theta, then that is the value your limit is. Let's do one final example. Does the following exist? X cubed plus y cubed over x squared plus y squared. So maybe does someone want to volunteer? So this should be 2, 0, 0. Does someone want to volunteer just to refresh our memory? What are x and y in polar coordinates? How do you get the expression for x in polar coordinates in terms of r and theta, and what's y in terms of r and theta? Right. So if we convert this in polar, if this is our function f, then in polar coordinates, we have up top r cosine theta all cubed plus r sine theta all cubed over r squared again. So this is r cubed cos cubed theta plus sine cubed theta over r squared, which is r times cos cubed theta plus sine cubed theta. Now, what's the limit as r goes to 0? Right, as r goes to 0, this is 0. Technically, right, what you could say is there is still a dependency on theta here, right, which might concern you, because here there was absolutely no no dependency on theta. So whatever path you come in at, you could write your path, imagine your path given in r and theta coordinates. It just completely does not pick up what theta is. In this case, that's not quite true, but you do know that you could kind of squeeze this thing, right? This quantity here, cos is always less than or equal to 1, between -1 and 1. This is also between -1 and 1. So you have the following bound. This is something like 2r and minus 2r, right? Because if this is greater than, this is between -1 and 1, this is between -1 and 1, this is the same, then in fact, they could never be 1 at the same time. So this is actually a bound like this, but that's a subtlety. You're always trapped between 1 plus 1 and -1 minus 1. So this quantity here is between 2r and minus 2r. And as r goes to 0, regardless of behavior in theta, you get these go to 0. So this means that what you actually want goes to 0, which means that, well, what was this? This was your original function, which means that the original function here goes to 0. So -2r and 2r are bounds because, once again, cosine and sine are stuck between -1 and 1 each, right? So you could imagine the largest this could be is 1. I mean, 1 cubed is 1, right? The largest this could be is 1, so these are 2. So this quantity here in parentheses are, between -2 and 2. This is r, so you trap these between here. But of course, sine and cos can never be 1 at the same time, right? That just isn't what sine and cos work. So technically, you can't. It's not less than or equal to. It's just always less than 2 because you can never be 1 at the same time. But that's minor, right? We don't really care about that. When we take r equals, the big thing is we've trapped it. We've sort of squeezed this thing between these two quantities, and when r goes to 0, the squeezed thing goes to 0. All right. So in this case, right. So above this was So cos theta and sine theta. So a technicality in this case was you can't, because there's theta in this case. It was not as direct as our earlier version where there was no theta at all. So whatever path you take, no matter where theta winds in your path, this didn't care about theta. This is technically not agnostic towards theta, right? Theta still appears here. But what I'm trying to say is, no matter what path you take now, regardless of how theta winds, as long as you look at r goes to 0, which is what every single path towards the origin has to satisfy, r has to go to 0. This is true, and hence you could conclude this. Okay. Any other questions? All right, we'll continue next time with derivatives, partial derivatives.